Perfect.
Once you get the thumbs up from Colin, you're good to go.
Okay. So I already introduced myself. Again, Pluralsight, Lightbend. I actually have a C# background. I actually have found that C# to Scala is a easier jump than Java to Scala. Most people that I've talked to have agreed with that. The only thing is that Java is starting to catch up, so it'll be a little bit easier. Lambdas, Java 10 now has limited type inference. Forget some of the other stuff that they have that they're getting there little by little. All right, so we're here for Apache Spark. I had my Mac there, and the HDMI port, like even without moving it at all, it would just go out. So then I had to pull out my VGA adapter, which I didn't learn because I didn't bring it. But now I'm going to start bringing a VGA cord. So I have an adapter so I can do a VGA and try to be dynamic. But they didn't have they had to actually call somebody to bring a VGA cord over, which usually you at least have HDMI and VGA. But. All right, so we're back up. So why not just use grep? Grep is great. Actually, if you have a small data set, I would say use grep. It's on one machine. It's actually pretty darn fast. But once you get to big data, maybe not so much. So why not Hadoop? Hadoop basically says, okay, we're going to take all that grep stuff for the most part and run it across the clusters. I mean, you could say what you want to say about it, MapReduce, this or that. I mean, you're running grep in giant clusters. All right, so now we're much faster. So we're good, right? Has anybody ever written Hadoop? Well, that's good. I mean, most people haven't. To be honest, I haven't, but I've seen it, and it's not pretty. Partially it was Java, and so there's comparisons. Java, Scala. Scala is a lot more terse. So along comes Spark. Spark does basically the same thing. So here we had, like 4 different pictures that I put together, and here we just have one. And it's even faster. So you're doing it on less machines at a faster speed. So that's why we want to use Spark. So big data doesn't necessarily mean big code. There's a reason that I made it so you can't read this. I mean, it's just, this is not maintainable. So this is Hadoop, basically. So we don't want that. What do we want? We want smaller code. So this is basically the same thing. So the core of the logic right here, it's 4 lines of code. Done here, here, and here. It's strewn all about. There's different places. It's just a mess. Whereas here we say, okay, read in a text file, flat map it to kind of flatten everything, count by value, and then save it off. So you've done all of that in 4 lines of code. All right, so further to some additional items here. Spark, the minimalistic code makes for better readability. As well as it's much more expressive. There's different things that you can say attributed to that. The small code itself, lost my train of thought. But yeah, so the smaller code, lambdas, things like that. All of the joys of really Scala you get out of Spark. And they've done a good job of porting that into the other libraries that they have, Java and Python and whatnot too. It's fast. There's actually a reason that its magnitude's faster. One, they've put a lot of time and effort into that. 2, it runs on memory for part of it, and we will get to that. But that was really its biggest claim to fame. There's a lot of things that differentiated it. But the fact that it could do things in memory and store things in memory really is the thing that made it leaps and bounds better than Hadoop. Yeah.
I'm new to Spark, but I thought Spark was just the memory portion, but the persistent layer had to be Hadoop or something else. Or is that too early to ask the question?
So no, so that's fine. So whenever I say in memory, That's working with your data in memory. You still want to persist it to, they still have their back end to some extent in HDFS, but that's not, you don't have to. Actually, you could do a S3, just see like regular disk store, Elastic, anywhere or wherever you want, and we'll actually get to that. Testability. So one thing that was really, really hard with Hadoop was testability, because it was your code was so intermeshed with everything else that you had to basically spin up a little mini Hadoop cluster just to test it. Whereas Spark, they've actually abstracted a lot of that out, and you can actually write your code into separate modules and things like that. So it makes it much easier to test. It's interactive too. So this again comes in part because of Scala. So they've taken the Scala shell, and you can actually say Spark-shell, and I should have a little bit of time to show that at the end here. But you run Spark-shell, and all of a sudden you can start testing out against local databases. Really, you can even point to your cluster and test against real data if you want to, or if you have like a test cluster too. But you can start interacting it, getting answers immediately, see how code works and things like that. Fault tolerant. So it's built with fault tolerance in mind, and that's something we'll get to as we go through it. As well as it unifies big data. So what does the unified big data mean? There's what's called the Hadoop MapReduce explosion. So if you're using Hadoop, then, okay, now all of a sudden you want to kind of start streaming it a little bit. So you're going to want to pull in some storm stuff. All right, so what if you want to pull in a little bit of the Scala world to Hadoop? And there's scalding. Hive is kind of like a SQL backend for Hadoop. Mahal for machine learning, drill, so many things. So again, you're using Hadoop, but now all of a sudden you've exploded, and now you need to learn all these other things if you want to really find use in it. So Spark brings that all together, and you end up with what they called a unified platform for big data. So that means everything's really built on Spark Core. That's the origins of it. We'll get to it, but they use things called RDDs, and everything is built on top of that. So what I mean is now they have Spark SQL. Underneath it is RDDs and kind of that batch layer and that resiliency that's there. Same thing, Spark Streaming, MLlib, GraphX, and on top of that is really DataFrames and datasets. That's where they're building in today's world. Some of these are a little dated, and we'll kind of get to that. So like Spark Streaming is now using DataFrames datasets. So they have an older version of Spark Streaming, but now they have a better version of it. GraphX isn't really maintained anymore quite so well. It's still there, but we'll get to that. As well as the Databricks pops up. Databricks is the company that, so the founder, the guy who created Spark was Matei Zaharia, and he comes out of, why am I drawing a blank on the name? Out of California, UC Berkeley. So he came out of there, and really a lot of the work he did was out of what's called the AMP lab, Algorithms, Machine, and People lab. So a lot of funding there. And I think, if I recall, he actually built he worked on Mesosphere and started doing Spark as a toy project, and it really blew up. And he saw a lot of potential there. So then Databricks comes along and adds that production stability. So it's open source, but Databricks is now probably over 50% of the contributors. In that stability, can't really read it here, but Spark, they tell you Spark 1.3 is binary compatible with Spark 1X releases. So they try to keep binary compatibility across the major releases. Not even just like anything else. This is actual binary compatibility. They tell you the things that do change, as well as they have their MIMA tests that actually tell you if somebody makes a code change, then it flags it and will say, hey, this is changing a public API, so you can't do that in this version. It has to be, basically there has to be an override to that. So that's pretty cool. As well as in that stability world, this has actually fallen a little bit as of late. I think they're getting back to it a little bit more, but they were following drop things and make sure you release on a regular time frame. So they would do 1.3, and that meant it was for 1 quarter. 1.4 meant the next quarter. 1.5 next quarter. Once they went to the 2 series, they had a lot of trouble getting into the 2 series, getting the things that they wanted, and they've faltered a little bit. But now they seem to be back on a cadence. Just the regular slide here. I'm going to go through it real quick for time. But who's using Spark? I mean, this is even potentially outdated. I could add some, probably even bigger names onto here, but you've got just tons of stuff. We've already went over real quick. Scala is the main language because it was written in Scala. And because of that, you automatically get Java. But one thing about Scala, if it was written in Scala first, a lot of times your Java APIs have, that it's not perfect because, I mean, Scala, to make Scala work, it has to write JVM code that Java isn't pretty in Java per se, but they've actually spent time and they make sure to expose the public APIs in a nice fashion for Java, as well as Python. And then they also added R. The nice thing about R is that R by itself is kind of your own data science language, but it's a single node thing. So Spark allows you to write R and boost it out into real world. However, still, last I heard, Scala and Python are their biggest in any surveys that I've seen. Most people use it either in Scala or Python. Java growing a little bit, but yeah, those are the 2 that I've seen. Big data, it kind of gets to something that I was saying before. Make sure that you actually have big data. If you only have like maybe 100 gigabytes or something like that, you probably could even, nowadays in most machines, you could probably get through that pretty quickly in something else. There's some articles about big data or writing a grep for it or something like that. So you want to make sure to use the right tool. So just because I'm advocating Spark doesn't necessarily mean it's the right thing for you. So Spark Core, like I said, that's really where Spark, the root of everything comes from. So what you have is, we're going to give just the high level of how Spark works. So everything's run off of a driver here. And if you want resiliency, you can use things like Zookeeper and whatever that are based off your cluster. But I'm not going to get at the high level resiliency at the driver level. But you do get resiliency across your workers. So you can say, hey, the driver is going to be the thing that manages who gets tasks and who has what data and whatever. So it's going to shoot for data locality. So it's going to say, hey, this worker was working on, we know that things were partitioned. So it works on things A through D. So I'm going to shove everything that's A through D over here. So that way you send it over here, but the data that it needs is over here. So it still has to make calls. So it's going to try to keep it as local as possible. So inside of there is called a Spark context. That's basically the thing that runs the driver. Nowadays, actually, I forgot to update this. Spark context is still there, but they found that confusing as they got into things like SQL and things like that. So they actually changed this to be Spark session. Ultimately, it's still the same thing, but it's just saying, here's your session. Spark, you can, in fact, get to the original Spark context with sparksession.sc, and it gives you the Spark context. Actually, I'll get to it later, so we'll get to that. The Spark context is kind of the orchestrator of everything. So it'll create the tasks, it'll schedule the work across, and again, it'll shoot for data locality, as well as handle any kind of faults that may happen. So it'll reshift work if a node goes down. And we'll see that. The ultimate thing that happens here, the core abstraction is called an RDD. Even if whenever I said it all kind of went SQL, this, that, MLlib, streaming, GraphX, and now to DataFrames. Even still, DataFrames is built on top of RDDs. But again, these are things we'll get to. So an RDD is a collection of elements partitioned across the nodes of the cluster that can be operated on in parallel. So mumbo jumbo, what does that mean? Means that it's a resilient distributed data set. Oh, my stuff's off. Oh well, that's meant to circle a data set. So a data set, so I mean, it's pretty simple. It's saying it's storing your data. It's distributed. You know, let's just get rid of those. So it's distributed. And so we've already gone over that. We know that it's going to distribute the work from however many nodes as you have partitioned your cluster into and told the Spark worker to work on, as well as it's resilient. So if something working on a particular task goes down, then it's actually going to spin it back up. But it actually works off of, do I have it in there? No, I don't. So this is just going with that it's lazy. Actually, this does get to it. So it is a lazy thing, and it's built off of what's called a DAG, directed acyclic graph. And so the reason that that's useful is that, and the reason that the laziness is useful is that it'll build out you say what you want it to do, and then it'll optimize as much as it can. Especially once we get to DataFrames and datasets, it gets really, you can do tons of great things without having to worry about performance. The Spark optimizer will handle it for you. But as far as the resiliency goes, if something goes down, it's going to say, okay, I know that I had a certain amount of data that was there. And because of that graph, I can start from a certain checkpoint or something like that. So you can, if you set up, in fact, the Spark streaming originally used checkpointing automatically behind the scenes, where it would say, okay, instead of starting, say you said that you have to do a map, a reduce, a map, blah, blah, blah. So we'll just call it A, B, C, D. If it crashed on D, but it's stored off at C, so it can say, hey, I have the graph at this point. You can just take off from D. So it saves that time and you don't have to redo the whole thing. And even if it does have to go to the origination point, it knows the data set it was working on, and so it doesn't do the whole thing across the whole cluster. It knows it locality-wise. So I do have DAG there. Transformations, so it can do things like map, filter, and things like that. Like I said, I'm not going to get into too much of the code. But then the other thing that they split it into things, transformations, which transformations are your lazy aspects. Actions are whenever you're actually doing something. So anytime that you say collect or save or count or something like that, it's actually going to act on that. So all along the way, so if you run map, filter, blah, 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 it actually won't do anything. It'll just be building that graph so that it knows what to do. Whenever you call collect, so collect back to the driver, which that's one thing you don't necessarily want to call unless you've reduced your data set. So if you have things split out across 3 clusters for a reason, unless you've reduced it down to a manageable level, if you call collect, it all goes back to the driver, and you could get out of memory just because it's distributed for a reason. So all these things require the data to come back and do something and give an actual output. If you're working with the data, if you get back, if the return type is of type RDD string or RDD tuple string int or whatever, if it's wrapped in an RDD, it's a transformation. It's lazy because it's still in that RDD state. If it gives you the data back, so instead of an RDD of string, you get the string, a collection of strings or something like that, then it's an action. That's one way to tell. So you've got your reduce in there too. All right, so going back to our mechanics here, now we talk about the workers. So the workers have different executors that are going to do different things, and you can even parallelize within there. So your workers are kind of your machines, and in here you have kind of your threads that are running. So what it's going to do is it's going to have these tasks, and it's going to disseminate them out to the different workers. And let's say that these finish and all of them finish, and then all of a sudden they're going to, then this one here crashes. So what's going to happen? Instead of having to do the whole thing again, this one restarts, or maybe a new one pops up or whatever. Now it's going to send the task down there and say, hey, this is where you were, and it's going to be able to finish up and go right from there. So all of these remained in a good state. You didn't have to redo everything. You just had to do that one specific thing, get it back up to state, and then you're good. All right, so getting to your question about input, or actually you were talking about output. I think I have a slide on output. So as far as input, there's tons of things. I mean, if you can think it, they probably support it, but just to name a few, you could read from the file system, Hadoop, S3, just a regular JDBC database, Cassandra, as well as we'll get to memory, so you can read off of memory. In fact, I haven't stayed as much up to date on it, but they had one of the things they had was a memory file system that they were working on, but now I'm actually forgetting the name of it. If it pops up, Tachyon, that's what it is. So Tachyon, it's kind of like basically saying, hey, we can store, memory is becoming cheaper and cheaper, so we can actually store a ton of data and almost have it be persistent. Now, I think they still have an underlying true persistence layer, but they really boost it to a even higher level if you're using Tachyon. Different structures, Parquet, Avro, things like that. All right, so I've been talking about how it can work off of memory. So how does that work? So I have my data, it's coming in 1, 2, 3, 4, 5, whatever. Then just pointing out that maybe it's a long running task. So then all of a sudden it's going to be 1, 4, 9. So it did its work. But again, it took all this time to actually run these each job. And I mean, if you're talking about truly big data, it's going to take a while. So now we do x plus 1, we do another thing, and we end up with this new data set. Now what happens if that crashes? We are going to have to some extent come back here unless we checkpointed or something. But we're going to have to come back here and start over, and this was a long task. So instead, we can say here, we can call cache or persist on the RDD. And so what will happen is asynchronously, this will go down and write to memory. Or you could write it to disk. So there's different ways that you could do caching. So a cache to disk is realistically more like a checkpoint because it's more persistent. But you can actually do cache to memory with overflow to disk. So it's all options that are available. There's different ones, as well as you can configure it to use things like backends like Tachyon and whatnot. So now, whenever it crashes, actually I missed the transition. So it writes it here. Now whenever it crashes, there should be an arrow going up. So it comes up from here, goes over to x plus 1. Okay. We can even change it now. If we're working interactively, we can say, okay, work off the same data set, do x plus 3. And it's actually going to come from here, go up, and it still skips this. So you can actually, there's something called the Spark job server, where you can sudo share your jobs. So if it's still in memory, you can say, hey, go hit this HTTP endpoint, and now you can run your own job, and the people don't have to worry about the length of time to do this thread.sleep and whatnot. So again, running off of cache is really useful from a speed perspective. Quickly, I'll go through kind of the different distribution and instrumentation mechanisms. Everything is expected to be run through Spark submit. So whenever I said there was a Spark-shell, that's really just Spark submit wrapped in a kind of a console. So it still goes out and does the same thing. It just makes it more interactive. So Spark submit says, hey, I have this jar that I've packaged. I've written up all my code, and I'm going to say, Spark submit, go run that, and you're going to pass the jar as the parameter and whatnot. And it's going to typically expects a main. I think you can even you can pass in a variable so that you can say the main method is actually called foo or whatever. But it's basically the entry point, And then it's going to go out and it's going to say, hey, I need to run this somewhere. And it's going to go out to this one cert, to the driver, which will run your tasks. Then from there, it's going to do the building of the RDD, the running of it, send all of the data out, and act on those results, whether that's collecting, counting, saving to S3, HDFS, whatever. And then it's going to complete and basically be done. So ultimately, Spark Submit at the core level is a batch type job. But again, we'll get to how we can do more of a real-time streaming type thing. The cluster managers that are available, actually that's in, let's just skip ahead. Okay, so there's Spark Standalone. However, that's not maintained too well. So actually, from a server perspective, most people are going to use something like Yarn, which is yet another resource negotiator. I think it's negotiator. And Apache Mesos, that's kind of the thing that's Lightbend is helping with, so we'll provide support around that for your management and things like that. So there's actually a company called Mesosphere that has something that makes Mesos even easier to use called DCOS. And then the other thing that I didn't add to the slide came very recently. Spark 2.3 was just released like less than a month ago or something like that. And they have experimental support of running Kubernetes natively. I haven't dug into it too much at this point, but I know everybody loves Kubernetes nowadays, so they invested some time in there as far as the thing that's going to manage all of your resources. I had stuff under there, so I removed it for this. All right, so that's the core. So underneath it all, you have an RDD. That's basically what I'm saying there. But now, on top of that, there's abstraction. So you can write your batch layer in RDDs, and that's nowadays an RDD is more akin to, I guess, writing C++. Now you're going to typically write things in Spark SQL and DataFrames and datasets, which also means it's called Spark SQL because now you can actually do something, say, hey, here's my data, register it against this table. And I think actually it's called register table now. I think they got rid of the temp. And then you can actually write SQL. So if you know SQL, I think they're up to SQL 2003 standards. And then you can actually write straight SQL and it'll parse it down into DataFrame/RDD logic. So from their own blog, as Spark continues to grow, we want to enable wider audiences beyond big data engineers to leverage the power of distributed processing. So all that's really saying is, if you're writing an RDD, you're still in MapReduce land. They've simplified it and made it easier to understand, but you still need to understand it a little bit more than maybe the typical data engineer. Whereas if you're writing SQL, it blows up, and now all of a sudden, people who didn't know how to write Scala can write SQL and be able to leverage everything that Spark offers. So kind of where Spark SQL came from, so the idea behind Hadoop, they had Hive, Apache Drill, and I believe Impala. So these are all kind of the competitors to kind of a SQL-ish big data thing. Spark SQL has, as far as I see it, blown them out of the water, especially lately. And the reason is because, actually I don't have that next. So we'll get to the reason in a second. So Hive, you can still point to Hive and it'll optimize. So you can write native Hive and that's great. But you can also write your Spark SQL and point it to Hive and it'll actually optimize the queries against Hive itself. You can even write Spark SQL to JSON, Parquet, just about everything nowadays, in fact. Amazon Redshift, Redshift is what I was thinking about before. And basically, again, everything that you can think of. So the reason that Spark SQL blows everybody out of the water is because of optimizations that it can make. So all the things, they've basically read all of these different database papers and learned from what the database world has already been doing, but now they've structured it into the big data world. So predicate pushdowns. If you write a filter, so if you write something that's like dataset, map, filter, but that filter, again, it's all lazy. So whenever the core goes to actually optimize this into the JVM code, it's going to sit there and say, okay, that filter that you wrote can go all the way down to the database layer. And instead of pulling it out, we can write that into, like if you're pointing to JDBC, it'll say, okay, rather than saying select all from foo, pulling it back in, doing a map, filter, it'll say, hey, that filter hasn't been touched yet. We can actually push that all the way down into there, and now it's going to be select all from foo where whatever your filter is. And so instead of getting a terabyte of data back, maybe you get like hundreds of gigabytes instead. Column pruning. So if you actually call, like you basically say, I want all my data, and then at the end of it, through all your maps and filters, and then even your projection, your final projection, you don't use like 20 of the columns. It's going to do that into the database layer. It's going to say select the specific columns that were used. And again, that's just something that limits the data. So whenever we're talking about terabytes or gigabytes, hundreds of gigabytes of data, if you're talking about limiting it by cutting half of the columns out because you're not using them, that's cutting your data down by half. And that's all going over the network. So that's kind of your slowest point at this point. As well as it provides a uniform API, and we'll get to that DataFrames data sets I've been alluding to. Yeah?
I'll freely admit that I'm a recovering database administrator. This optimization stuff is great in the database world,
Mm-hmm.
and there are all sorts of promises about SQL optimization.
Mm-hmm.
But at the end of the day, you end up having database administrators who really know their stuff, and you end up having quote-unquote SQL experts to optimize your queries.
Mm-hmm.
I haven't used Spark to any depth. I'm just a little not concerned. Sometimes these optimization engines,
Mm-hmm.
They tend to be oversold, and maybe.
Sure.
I mean, I've never used Spark, so I can't comment.
Yeah. So I've spent my fair time in the SQL world,
Okay.
In general, there's two paths, and we'll see that. But basically, you can say Spark SQL. You can write SQL, but you can also still write. First of all, if you really wanted to, you can go down to the data frame layer. But you can also write things, and I keep saying it, and we'll get to it, is data frames and data sets. You can still write map, filter, things like that. So you can still drop down, and you can even go back and forth if you really wanted to some extent. You can say, here's some SQL that I want to run against it. It'll optimize it into it. Okay, now I want to do X, Y, and Z. So I have seen some really, like basically people who, through doing support at Lightbend, I've seen people who have basically tried to port SQL into Spark SQL, and it's possible, but it's not exactly, you still should think about this stuff. Like if you're doing union, like I've seen some gnarly SQL code that people have tried to shove into Spark SQL, and it'll work. It's still not going to be optimized to perfection because, I mean, you still have to think a little bit about your code. And basically, if you've got like hundreds of lines of SQL code, you're probably doing something wrong, if you ask me. But that's the SQL world for a lot of people. So I'm not trying to bash on anybody who maybe has that, but it's things I've seen. But as far as code generation, we'll actually get to some of the stuff that they've done. It's phenomenal. I think they've actually taken some of the stuff that they've done in the database world. I think one of the things they've done, which is called whole stage code gen, is even better than what you would get with database optimizations. And we should get to that. But basically, this is everything that goes in. It's going to say, okay, it's going to say the logical plan, optimized logical plan. And there's actually UI where you can actually see the graph of what does what at what level. So you can see maybe where it's failing or whatever. So there's actually built-in monitoring, high level monitoring that you can get and dig into what's happening. Okay, so like I said, you can also go from SQL to really DataFrame to RDD to SQL. You can go back and forth all you want. So we've already seen this, but again, this is really where it's at. DataFrames, datasets. And we'll see what the difference is between DataFrames, datasets in a second. But this new API makes Spark programs more concise and easier to understand, and at the same time exposes more application semantics to the engine. So whenever you write RDDs, the engine will do a lot of cluster optimizations, but it doesn't do things like predicate pushdown, this and that, because ultimately it's a black box. In fact, I think I'll save that because I believe I have a slide for it. But a data frame is basically a table or two-dimensional array-like structure in which each column contains measurements on one variable and each row contains one case. So basically a data frame is a table, if you ask me. And that's what a data frame is. A data set starts adding types to it, and we'll get to that. But that's really the difference between data frames and data sets. Data frames are, so one of the nice things that I actually didn't add with RDDs is you get the compiler, unless you're writing in Python, I guess. But you get compiler errors. So if the types don't match up, then it's going to check it. If you're using data frames, that was the biggest pet peeve with people, was you still didn't catch compiler, like type checking type things. Datasets finds a nice middle ground of both worlds. So codability. So this is still much better than Hadoop. But now, I'm going to, for time, skip going over exactly what it does. In fact, you can see what it does now, because now we can say, and this gets to kind of your question, you can write it as a data frame where you say df.groupby, find the aggregate average age. Just the same, you can write the SQL. Select the name, the average age from df table, group by name. So whatever your flavor of preference is, you can go with there. In fact, one thing that's really nice and really shows the optimizations is that I'm doing a group by here. In general, you're not going to do a group by and just kind of leave it at that in an RDD world, because group bys are basically giant unions and things like that, and it's really expensive. But this a data frame group by, it actually knows that you're grouping by the name, you're pulling out the age, all those filters and predicate pushdowns, all those optimizations that I talked about. It can take advantage of and make that group by not be nasty. All right, so the future of Spark performance with more efficient storage options, advanced optimizers, and direct operations on serialized data. So this is another area that they've really optimized on, is they actually have gotten down to writing at the core level. They've written unsafe JVM. So there's java.unsafe.io or whatever. They actually have gone to a certain amount of byte management themselves, where they store the data in like a really compressed format, so that they can then even read it out without having to read the whole data back at points. They know, hey, here's a pointer to this specific point in the data. So it optimizes deserializing, serializing, things like that, and working against it. All right, so here, yeah, this is the slide that I wanted to go with here. So if you have an RDD, then you're going to say takes a string and does an ends with option. Then ultimately, it's a black box to the optimizer. I mean, it doesn't know that, it knows it's a type string. It doesn't really know what you're doing. It just knows that the output is going to be, ends with is going to be a Boolean. So it's going to say, here's something, and the output is going to be a Boolean. So again, all it really generates is an apply method, taking in a string, outputting a Boolean. Whereas now, if we say, okay, column X, so we give it a little bit of information it already knows about, but it's saying, hey, this is specific to this column, ends with post. Now it's going to actually write this thing that says ends with, and it's going to even say, hey, this is a constant post, so we can optimize there too. So ultimately it becomes faster, smaller, and smarter. We'll come back a little bit to the great optimizations in SQL, but I want to get to Spark streaming. So it's fast as well as it gets to pseudo exactly once. Because it's built on top of the fault tolerance that is RDD, then it allows it itself to be fault tolerant. If you are doing the transformations are exactly once because it's being managed and it's going to have these DAGs and RDDs that store things. Actions, if you fail inside of an action, it's still going to run it. It failed. It started to write something to the database. It's going to basically rewrite that same thing to the database. So you still want to point to item potency at the action level, but the transformations, you're not going to get a data set back that has A and A, as an example where A is your unique data set. But it's going to say, hey, it failed. It's not going to send back an A and then another A. It's going to send just that one back because of Spark streaming is, how many people here have heard of mini batch? Okay, so Spark streaming, this is the first level of Spark streaming. It has something called a D stream and for a discretized stream. And so it's not a true stream. It's basically, because it's built on top of RDDs, it's batched. So it's basically saying take a bunch of stuff and then shove it down to be processed, but it's doing it in mini batches. They've taken that level of the original Spark streaming to, I think they could get maybe in the less than, like around 100 milliseconds or so, which realistically works for a lot of your real data sets. It depends on your SLAs and things like that. So if you're maybe working at a credit card company or something like that, you want to do things a little bit faster. But most day-to-day work, you can get away with mini batch. But they actually have built it out, and we'll get to that too, to something called structured streaming. So the streaming landscape before was Storm. There's Kafka streams as well, Samza, Akka streams, and the real competitor is something called Flink. Flink, I think I have a quote from them here. No. I may duplicate myself here, but Flink, they wrote an article that basically said batching is just a subset of streaming. So basically you can think of it like, hey, we've thought of, just like RDDs or Spark made RDDs and everything with fault tolerance built into it. Flink has built an engine similar to Spark, where streaming it's native streaming. Now Spark, because of structured streaming, which again I'll get to, is something that Spark really went leaps and bounds above Hadoop, so it's gained tons of momentum. Flink, in my opinion, is never going to get fully past the early adopter phase, strictly because Spark has enough momentum and knows where its faults are that it's invested time in there that Flink doesn't. So again, Hadoop, Spark. So that's why people went to Spark. Spark, Flink, so it's not enough of a gap. And Spark is gaining on that. So realistically, to relearn something, as well as Spark has, we talked about it and we'll briefly talk about it, machine learning libraries that have things that are built in. So you don't need to learn a new thing. You can just say, hey, I know my Spark, I can write machine learning. Well, I know you still need to know machine learning, but they've optimized some of it, and I can write like my SQL, my streaming, my machine learning all as one basic layer. Whereas Flink is just still in infancy on building out machine learning and things like that. So it's just my opinion, but I don't think Flink's necessarily going to live. But as far as the original D streams go, basically you have all these data sources that can kind of be streamed in. They come into Spark streaming, And then, like I said, it's mini batching. So it's going to say RDD, RDD, and it's going to shove it through. It's going to hit the core, and then it's going to save out. Just because I'm looking at the time, I'm going to speed up a little bit here. But one of the libraries that, like I keep mentioning, is MLlib. They've built that on top. So that was originally on top of RDDs. They've now started to build it out on top of, here we go. They've started to build it on top of DataFrames and datasets. So it's even, you get the optimizations there, as well as from a machine learning side, they know more about your data. They can even optimize on the machine learning side of the algorithms. Let's see. So things that are there, they've got classification algorithms, regression algorithms, collaborative filtering, clustering, dimensional reduction, feature extraction, transformation. Things that you can do with it are anti-spam, fraud alerts for credit cards or whatever, approval ratings, your cluster graphs. I think that's using k-means, something like that, as well as kind of getting just analytics out of things. GraphX, I'm just going to merely say that there is something called GraphX. They created something called GraphFrames, which builds on DataFrames again, but I haven't seen too much growth there, so I'm just going to kind of pretty much, actually, yeah, skip it. So now let's go to kind of the next generation of things. So that was all Spark 1X, and it's useful to kind of know where it's coming from, and still it has a lot of relevance. I've seen a lot of Stack Overflow questions that still are using RDDs. But here, let's get to what Lightbend is focused on is big data is this big blobby thing. But nowadays, most people want fast data. They want to see it, basically, they want to see streaming at scale. So tons and tons of data, now streaming. So that's where the world's moving to. So Lightbend likes fast data. So now we're talking about even more data. So what is fast data? Basically, we're going to say, hey, big data was, we're doing all this processing, and then we go through and we get a result. Hey, yay. But big slow data. Even with Spark, it's still, I mean, you're talking about batching. You have to set up something that's going to process it or re-kick it off or whatever. So what's better? Big fast data. So again, whenever we say fast data, it's really big fast data is what I'm referring to. And so the difference here is you have your same thing. You've got your cluster, your incoming data, and then basically you have, okay, got my answer, got my answer, got my answer. It's going to kind of keep processing, and nothing stops. It's streaming through. And so again, that's kind of what I was saying, that batch is really just a subset of streaming. Just things that you can do with fast data type stuff. We're going to skip that for time. All right, so structured streaming. So I went over what D-streams are, and D-streams are still useful because I think structured streaming has gone leaps and bounds, but it's still somewhat in its infancy. But structured streaming is definitely the next level of things. So simplest way to perform streaming analytics is not to have to stream, or is not having to reason about streaming at all. So how many people here know about streaming windows and dealing with state across your streams and things like that? Anybody have to deal with streaming stuff and state and all mutability or anything like that? So it would be a question or yes?
Question.
Go ahead.
So just because I'm sort of behind on this, so what do you mean, what's streaming data in this context? So I get like Twitter, that stuff, but what other sorts of things maybe within a business, isn't Twitter and stuff like that, would be considered streaming?
So let me put it in a difference between streaming and batch is the better way to put it. So batch is saying, I have all this data, and I'm going to take it from time A to time B and shove it in, process it, and then later on I say, okay, I was at B, I'm going to do this, and it's just manually kicked off, and it's just a job that says, here's all my data all at once, go process through it, okay? Whereas streaming is basically saying, here's A, start processing it, it'll start processing it, and then B comes in and it just basically it's continuous processing versus batch processing. That's probably the best way to really think about it. Is batch processing is stuttery. Whenever I say streaming and things like that, it's the same thing. It's just saying you don't have to wait for it to come in. So first of all, maybe you say, hey, I wait every hour, I'm going to run a batch job. Here you could, like I said, for D streams, you could get down to check every 100 milliseconds. So actually continuously stream. The program theoretically never stops. It's going to keep going, keep processing, doing all of your big data stuff. And one of the hard things with streaming is machine learning. That's one thing that Databricks is and Spark is taking on, is saying, hey, we can actually kind of on the fly rejigger your data model with this new data, and then shove it back into the stream, and now you have this updated algorithm to check against.
So that kind of answers my question. So say you're doing a k-means clustering or whatever, does it like come up with a value and then like every millisecond or whatever, it's constantly like calculating what the clusters are or whatever?
As far as I understand it, I will say machine learning is my weakest point, so I can speak of it, but not really that deep. But I have seen some algorithms that they've written with streaming where they can get real-time prediction analysis across and in fact, they made a mistake at one of the Spark summits. They did rather than grabbing a data set for their keynote talk and pretending to do stuff and having real data, but they hooked up to the Twitter stream. And there was some profanity on the screen, but it was because it was picking out things like that realistically fit the algorithm, and it was constantly adapting and things like that. So if it can constantly adapt and basically say, hey, here's the model, it's stored off, grab it, store it, grab it, store it, that type of thing.
Just along the same lines of some of the more sophisticated people, what they're doing is actually sample a stream.
Mm-hmm.
And things like bloom filters and so on and so forth. So you can sample the data, and if you give it, I'm willing to tolerate a 5% error or a 10% error, and given that means you can sample the data less. So there are sampling techniques that you can add to your stream in case you can't keep up with the torrent.
Yeah. All right, just to move on, because I was hoping to be about an hour, but I probably will end up being about an hour and a half, and then do live and any additional questions. So whenever we get to the difference here, so if I wrote a data frame, select the name, age, where, age 21. The nice thing about the new age of streaming is now here we said, okay, so this is your core logic, your primary logic. And then here you're saying Spark, read, and it's in the format JSON, and then load it. And then here you're saying output write format that you're trying to and saving it. Okay? Primary logic of your streaming logic. So the one thing that I was saying before is streaming has the idea of windows and windows of time that you're working on and whatever. For the most part, Spark streaming or structured streaming has tried to get so that you don't have to worry about that. So your core logic stays the same. And if now all you have to do is say read stream, write the stream, and start. So you're keeping basically the same logic as your batch logic, and you're changing like 3 lines of code. So it's actually much easier that way. So again, this is just pointing out that it's really just continuous processing. You can take kind of the subsets of data at a time. So you get a streamlined API. So I didn't really actually go over, I thought that I must have either gotten out of order or taken stuff out, because like I said, I didn't want to go too low level. But DataFrames are kind of the best of both worlds, where you have or actually datasets are the best of DataFrames, which we're getting to here. But DataFrames allows you to do what I was saying, is write SQL or write your map logic. So it still allows you to write functional logic if you want to drop down to the RDD level, and then come back to the data frame and write things at a more SQL-like fashion where you're telling the engine what you want, not how to do it. But then, so data frames were great, but people complained about the typedness. So from a functional aspect, you could say, hey, drop down from a row. So that's what data frame store is, a row. And so a row is just, hey, here's an object. It's your row in your table. We know kind of stuff about it, but we can't guarantee the types and this and that. So that's what a data frame is. Whereas now, that's just the new stuff. So like I said, Spark session. Actually, hold on. A data set itself can be typed. So you could say, instead of being this amorphic kind of row thing, you could say data set that is of type maybe a tuple of 3. So it's a string, an integer, a string, or something like that. So you can actually do that and work on your data. Now, whenever you call map, it's actually going to type check it and things like that. And it's still, for a certain level, they then still are able to get the logic out of it. But if you start to go to the functional level of things, you do start to go back into the black box territory a little bit, because again, you're writing raw code and it doesn't know what that is. Okay. So one of the things that they have is called tungsten. That's kind of the catalyst optimizer. That's the thing that figures out what you want your code to be doing and how to optimize it. So in Spark 2, they added what's called whole stage code gen. Actually, as long as I didn't get rid of that too. I'll show you how that changes things. I have a nice graphic for that. But basically, it speeds up your processing. Because one thing that RDDs that they could do, and data frames and all that, is they could say, hey, I'm going to run a map and a map, and it's going to do those and combine them into like kind of one. It's going to pigtail them together. So it's going to say, take the output and don't do all of it together. Take almost a stream of maps. So it's going to say map, get the output, shove it down to the next map until you get to an action or something that has to pull it together. And it's going to do it kind of one at a time so that you get kind of that optimization. You don't have to say, do a bunch of stuff. Okay, now do the next map. Now the next map. It can just say flow through, flow through, flow through, which reduces on virtual calls and things like that. And again, we'll get to what whole stage code gen is, but the biggest thing you get there is even as fast as Spark is, they got 5 to 10 times speed ups. And basically, you can think of Spark as a compiler. It's kind of almost jitting as you go. Spark 2, they expanded SQL accumulators. So if you need to accumulate data, there's a specific API out there for it. They simplified that in the newer versions. Data frame focused machine learning. So like I said, it used to be based on RDDs. Now their machine learning libraries are based on data frames. So you get a lot of benefits of all of that. Scala 2.11 is the de facto, so it used to be Scala 2.10. In fact, we're trying to get them to go up to Scala 2.12, but there's some resistance there. But again, it gets to that they're trying to go with compatibility and things like that. So if you up the versions, then you have to change some stuff. All right, so Spark SQL, why datasets? So here we have the RDD. It's great, it's type checked, but it's a black box. Data frames, great. Now we have this catalyst optimization, but it's not type checked. So that's where, like I said, why we like data sets is because it's kind of giving you the best of both worlds. It's giving you this engine and it's type checking. A data set is a strongly typed immutable collection of objects that are mapped to a relational schema. So basically it's strongly typed, but it's still this relational schema. So you can, whenever you throw in that relational schema, it means that it knows certain things about it and you can optimize. So again, it's building the two worlds together. So this is what I was saying before that, okay, so data set of my class. So now you can actually do that. But if you want to, you could still do a data frame. So anytime you see in the API data frame, it means that it's really a data set of this amorphic row. Okay, so a little bit more of why is basically if I write this code that says, hey, my schema is of Boolean type, I'm going to parallelize it, and you see that the row, it's a 0, true, so it's got an integer, a Boolean, a string. So whenever you create the data frame, you actually call collect, and then at runtime, you're going to get a class cast exception. With datasets, all you do is change it to a dataset. Now it's going to give you it's going to actually realize that these aren't right, and it's going to actually give you a compiler error. So the nice thing is, combines functional with relational, you get this nice middle ground. Okay, as well as still faster compression, things that we've already talked about. Coming back to Spark streaming, these streams. So from a flow perspective, you may see this being a little disjointed. I actually had combined all of my how-tos of Spark that have changed over the time and tried to shove them together, but as you can see, some of them fell out of order. But these streams, we've already kind of gone over it, that this chunk of time is going to be in this RDD. Then you're going to have 1 second, 2 second, 3 second, all that stuff. And so along the way, it basically just shoves things down into these functions. So it's going to be running against Spark Core. And along the way, it's saving and printing. So here it's going to save. And at the same time, while it's kind of saving, it's still gathering this data. So it's doing stuff down here, but it's gathering, now it's still gathering the data. So that's really what we're talking about these RDDs of things. So it's storing it into this block of data set that can be understood better. And then all of a sudden this finishes. Now it can go through and finish the rest of it. It can grab the next batch. Stateful streaming. Basically, actually for time, I'm going to skip that. And again, if you feel necessary, we can dig more into streaming and things like that at kind of the training that I have set up in a few weeks. Wasn't sure if I'd have enough time, so I wanted to at least have it there. Checkpointing is an important thing to understand with D streams, though. And really, RDDs, you can throw it in yourself. But basically, you have this thing that's built this whole giant thing up to n plus 1, and all of a sudden it crashes. You don't want to have to start your stream again and do 1, 2, 3, 4, etc. So it's going to take all that time to rebuild where your data was at. Whereas Spark streaming is going to say, okay, I have 1. It's going to checkpoint it, go 2. All of that's asynchronous, so the checkpointing is asynchronous, and it's going to build it out. Now, whenever it fails, it's going to have these checkpoints that it's going to build out, and instead it's going to start from here. So it's similar to how it works off of caching in memory, except this is more persistent. And it's going to say, hey, start from here and start building up again. So that was D streams. Actually, oh yeah. Actually, that should say structured streaming, but either way. We're actually going to skip that for time. Okay, so structured streaming is going to say, hey, we have this stream of data. So we have the idea of data frames. But now, instead of thinking about it as this block of data, it's going to be some data, then some more data. So it's going to keep coming in, flowing in. But it's the same logic that we had before. So we've already seen this. Actually, I could have just cut this out. So read stream, write stream instead, and start. Okay, so one thing that you get from structured streaming is you get the catalyst optimizer, as well as you get, it's a one-to-one graph. So for the most part, if you use certain data sets, so Kafka with offsets and even writing out to Kafka, I forget the certain things, but if you use specific data sets that have guarantees, then you can have exactly once. So basically saying, okay, if you use Kafka, it's going to say, hey, it failed, and then it's going to rewrite the data, and it's going to say, hey, you go to this offset in Kafka, and it's going to natively know, okay, where I'm reading from is from the right point. I know that this is the last place that I have the data, and even outputting it, it's going to say, okay, here's the offset that it was going to. I know that that hasn't been written. I can rewrite it. So they have, to a limited subset of things, you can have exactly one streaming. As well as they have real-time, or as of Spark 2.3, they have real-time streaming. So D-streams, we said, was you could get about 100 milliseconds because it's all batched together. They actually have a way to turn on what they call continuous processing in datasets. And it reconfigures the code so that actually it feeds it in, and it's actually a real-time stream. And I think they've gotten it down to like ones of milliseconds or something like that. So they basically have said, hey, with structured streaming, you can write this SQL-like code and be processing it all the time as it comes in. So the difference between as it comes in streaming and batch streaming is batch is saying, hey, we're not going to process it until we get to this point. Whereas real-time continuous streaming is saying, we got an object, process it. We got an object, process it. We got an object, process it. And so they had to do some work to make sure that the exactly once and things like that, the guarantees that they had would remain even in continuous. But there's still some unsupported operations within structured streaming because then you lose some of those guarantees. So you can kind of see, and I believe the compiler will yell at you for stuff like that, but it's still somewhat in its experimental phase. I think technically it is listed as experimental in 2.3 still. Now, in the Spark 2 series, originally, let's go here. Originally, we said Spark was built and memory, like writing back and forth to the disk, was the bottleneck. So Spark was great. It said, hey, here, we're going to grow here. The internet was kind of a bottleneck too, but now the internet is actually pretty darn fast, especially within companies. So now the processing is your slow point. So you're running these complex algorithms. And so their focus in the Spark 2 series is how can we optimize your code even more than like DataFrames and things like that. So what they've done, as well as the focus is on continuous processing. So what they've done is, this is what I was talking about before, and it's really cool. So the typical process in even the database world is called a volcano model. So what that means is, okay, yeah, so you get your data. I thought I had the text there first. And you're going to transform it. And so we saw that there was a ton of data down here. It shoves one thing up, and this is what I was talking about. It's going to do that one thing, and it's going to transform. It's going to filter. It's going to aggregate it, and then all of a sudden it projects it out. So it's doing that kind of one at a time type thing. But it's called volcano because it's kind of spiraling up and then finally spewing out. So it's called the volcano model. You can actually look it up. There's whole papers written on it. But the idea with whole stage code gen is now, instead of really worrying about all of that, the idea was you have all these virtual calls that happened, right? And so it would run through a map virtual call, this and that and this and that. So you have our transformation, we had our filter, we have the loop that's going through there, and that was all virtual calls to different things. Whereas now, whole stage code gen, now that they can see your code better, they actually said, okay, what would, if you just went to a grad student and said, write this, here's your business logic, write something for it. They'd write this for loop. They wouldn't write, here's a call to this, here's a call to this, here's a call to this. They'd write this for loop probably. And it turns out that because you get rid of all these virtual calls, this is as I pointed out, like 5 to 10. In fact, I think if you really want to jump the gun, I think there were some spots where it was like 100 times faster, because you're avoiding all the overhead, and you're just saying, hey, all of those things can be boiled down into this simple logic. And so whenever I said Spark as a compiler, basically you say what you want it to do, and it's going to write this instead. So it's going to basically say, hey, this is much more optimized code. I can get rid of all of those extra steps and just boil them into one thing. And that's why they're calling it whole stage code gen. So again, it talks about like the different aspects of it. Yeah, so 5 to actually 100 times faster. Now, this is a bit outdated, but I kept it here just so I could talk about it real quick. Actually, I already kind of touched on it, but here's the important part is something called Drizzle, which basically gives them the continuous processing. And it just came out last month, but in Spark 2.3, continuous processing is something you can turn on. It's very experimental. I wouldn't necessarily do it in production, but if you need that real-time, like milliseconds, not even 100 milliseconds of response time within your processing, then you can turn on continuous processing. And their whole focus is on structured streaming. So they're still working on machine learning. They're still working on all that stuff. But their focus is realistically, hey, Flink came out, like I said, hey, all of this batch stuff, it's really just a subset of streaming. So Spark came along and said, hey, we're going to embrace that and write all of your code, your data frame code that was batchy and that had all the optimizations in it that we had built in. Now we created structured streaming so that all you have to do is change it to start stream and or read stream, write stream, and start, instead of load and read and write. So their focus is optimizing this and being able to work with, as I mentioned, windows of data and some of the things that you have to do with structured or with streaming, but they're going to try to make it so that you don't have to think about it. Just like with RDDs and then to DataFrames and datasets, they're trying to make it so that you don't have to think about those low levels anymore. You just have to write your business logic, and that's really what their focus is. As well as there's going to be a lot of stuff that comes out of Rise Lab. So I mentioned before that Spark came out of something called AmpLab, and so that was like government funded. They got a lot of grant funding and out of UC Berkeley, and so algorithms, machine, people. Whereas Rise Lab is the AmpLab ended. Their grant was done, so they redid things and they created Rise. So that is real-time. S is for security. I don't remember Rise Lab as well because it's relatively newer. But it gets to basically your streaming things, your security things. Again, I forget what the I and E are, but I'm pretty sure R is for real-time and S is for security. And so that's really where a lot of the new things are going to be focused on in Spark, because they're going to feed that into Spark essentially. All right, so I kind of breezed through it at the end, but again, I wanted to leave a little bit of time. I can take some questions first, or kind of show you the shell real quick if you want. Preferences? Anybody want to see the Spark shell and see it in action a little bit?
I'm a bit confused about the streaming. I'm wondering at what point does it actually give you the output? Because as I understand it, you're accepting this input and it's going out to workers and coming back with something. Then the process is never ever done.
So
you have to update for every single batch, each mini batch.
Yes. So it is actually writing out. So your logic, and in fact, the D stream will yell at you. So whenever we're talking about D streams, I think they wrote it into structured streaming too. But if you, so Spark is lazy, right? So if I wrote code, and I've seen Stack Overflow questions about this, where if I write code that says map, 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 and then I try to run that, I've seen questions where they're like, well, where's my output? It's actually a similar thing. So you have to actually have a save option or a collect or some kind of action for it to actually do something. So what it's going to do in the streaming cases, it's going to say map, map, map. And again, you have to think about it, and especially the D stream in the you have to think about it as that batch. And basically it's going to say, run through the data that it has, and maybe you have a print line or something, and then print that out. If it's going to be a save, it's going to run through the data that it has, and then it's going to save it to a database. So the item, the exactly once and things like that, especially if you have windows of data that are constantly shifting, but they're still using some of the similar data that was already there. You have to make sure that in your saves, you still have to think about item potency and things like that. Because every time that you call like save to the database, then it will finish. So for that batch, it'll finish, it'll save to the database. And then the next batch, it's going to say run through, save to the database, and it'll potentially overwrite old data because now it's old data too. So if something changed for something, then we want to write it out. Now, if you don't have something, if you're just on a constant append, then it can constantly be saving, and shoving. And just the same, you could even have your stream almost be like this circular thing where you say, hey, I have my stream coming in, and then I want to use stuff from the database. So you can have logic in there that says read from the database, and it's going to read from the database and use that data, which had been updated in the last round. So that's kind of where that machine learning comes into play, where it's saying, hey, the last batch saved it, and now whenever I go to use it, it's going to say, hey, here's the new data that I need to use to process against the new stream.
So like, let's say I had a constant stream of data. Like, let's say I was processing Ethernet packets, and
Sure.
TCP packets. With each mini batch, it's saving it. It's picking up where it kind of came out of it. So what I'm thinking is it starting that driver every time? Is it running it anew each time?
So the driver is actually a constant, long-lived thing in that case, but the tasks, it's going to kick off the core logic each time, yeah. So basically it's going to, like from the D stream, and really, I mean, whether you're talking D stream or even structured streaming to some extent, I haven't gotten into how they've implemented continuous streaming, but even the structured streaming was still basically mini batch-ish, where basically it's going to say, hey, go in and gather the data, and then basically it's running a little mini program. So all of that logic, it's still running it off onto the Spark workers, the same as if you had run it through cron jobs or something that would be constantly running.
Okay.
Make sense?
Yeah.
Could you explain more on the cache thing? And how is it cache? So how is it related to the laziness between the transformations and actions?
I think for that actually would be a good point too.
Because when I was playing with Spark, I was thinking that if we have after we do some transformations to Spark DataFrames, and if we want to reuse it again and again, then we should cache the data frame. Is that true?
If you are using something over and over again, yeah, you would want to cache it, because then if you're not kind of constantly rechanging things, then yeah, you are going to want to cache it, because why reprocess it over and over?
You just mentioned two types of cache, right? Cache to the disk and cache to the memory. So I was wondering, when I call that .cache function, is that cache to disk or cache?
By default, it's to disk. To disk with overflow, I believe. I'm sorry, I'm speaking before I think. To memory. By default, it's to memory whenever you call cache, but it takes parameters that you can override. But by default, if you just call cache, the default parameter is to memory with disk overflow. And if I can bump this up, which I thought was just... I've been spending more of my time in the Mac world than Windows world, so I forget how to bump the size up. So I do know if I right-click here.
Control plus, maybe?
That's what I did, and it just froze on me.
You need to go up to the little application menu, upper left corner.
Yeah, click on the command prompt icon.
I guess I shouldn't.
Properties.
we go. People could see that, right? Great. All right, Spark shell. Actually, it definitely isn't. And there's a lot of tickets in Spark where there's problems around it, and they actually don't care almost. Like there's just like there's one that's been ongoing where things just don't work right off the bat. In fact, Spark will not work right off the bat because of Spark. Well, Spark SQL won't work off the bat because of how it stores temporary tables for the shell. And you have to actually go out get this thing WinUtils, what that Hadoop uses and whatnot. And if people don't know that, then they get really confused. All right, so I believe that should do what I want. C.map. Actually, I can do exactly what I said. X2. Thread.sleep. We'll do it by a second. Actually, that's a lot of stuff. Hold on a second. That's not going to work at all. Se.make RDD. We'll say 1 to 10. And then we'll say 2.map thread.sleep. We'll sleep for a second. And then we'll do x plus 1.
I don't think you defined res2.
What?
I don't think you defined res2 there.
It's the shell. It automatically does. If you look one line above. So that should be good. So you'll see that this automatically returns. It did nothing. Now if I do res2.cache. Oops, that's not what I want. I want to do res3.cache because that's the new output. So now if I do res3.collect, should take about 10 seconds. There we go. So it actually distributed it, so it took less time than that. Now if I do res3.collect again, immediate. And I can even show that, and I'll show the UI real quick. Is how I said that it comes built in. Okay, so here we can see that it took 2 seconds for the first one, 36 milliseconds for the second call. And we can see even that storage, that in fact it cached it twice because I accidentally called cache on the wrong thing. But you can see that it's these things, and I have 8 cores, so cache partitions by default the Spark shell runs across your maximum. So it split it across 8. It's fully cached because, I mean, it gets to, if it can't cache at all, then it'll just spill over. So here it's saying it was able to fit it all in. And then realistically, we can come back to the jobs too, and we can dig into it, and we can say, okay, here's the graph that I was talking about, the DAG visualization, where it's saying okay, this is the whole, this gets a little bit to the stages. Now we're using RDDs, so you don't get whole stage code gen, but in DataFrames, stages come in handy. So here we're saying make RDD and map, and that's the stage. And I think it still remains the same even if it's cached. Yeah, so it's still going to look the same, but it's ultimately going to say, hey, the data that you're collecting was already cached, pull it out of the cache and whatever. And if I recall, it's the least frequently used, the cache. So that's the eviction pattern. So it will evict it out of cache if it runs out of memory. And if you've used it more recently, then you'll get that. Any other questions? Okay, so like I said, I wanted to just do it as a high level here.
Question, how's the debugging? Like, let's say I have some issue in one of the workers, or there's some data that doesn't fit the code for some reason. How does debugging work? Will it tell me which part of the RDD was broken, or?
So if you're talking exceptions, then yeah, it writes everything out to, in fact, I feel like I can go to executors and I can say even thread dump. So you could do kind of a live thing. And so see the thread dump. But, oh, it's because I don't actually have, if I had it set up to a cluster, you'd be able to see like the standard error, standard output, and it would give you actual, the errors or anything like that. So an exception should bubble up in those exceptions there. But I would say from looking at it from a data perspective, that's a different thing than an exception. If your data is not looking like you expect, that's where, in my opinion, the Spark shell comes in handy. Because you can actually say Spark shell you can pass in all these parameters, and one of them is your master. So the master URL by default is local use star, which is use all your cores. But you can actually have it point to Spark standalone, Mesos, Yarn. And like I said, they added Kubernetes recently. So you can actually say, hey, go point to my cluster, my actual cluster, and you could actually start checking out data. And you could run, so you could sit there and say, now let's say that I'm actually connected to my cluster. I could say, like I have tables or something like that. I can say Spark dot create data, or no, I want to do load. It's not create. I think it's load. Read. And then from there I can read, maybe it's in CSV format. I know I can say CSV, point to the file path or whatever, and then you can actually start munging your data, or you can actually even to take it to another level. You could say Spark shell and pass in your jar. That's your application logic, and you can then run actually invoke your classes and things like that. So again, that's where the interactive shell really can help you out.
All right, thanks. I think sometimes we just print the data out. Right?
Yeah.
Like print schema.
Yeah. But I mean, the nice thing is I could print it out here. I don't have to write it, I don't have to deploy it or whatever. I could. Now, again, different companies have different rules on where you can hit things, but if you're allowed to, you could just access maybe a test cluster or something. I don't know, but yeah. And then you can do make RDD 1 to 10, and here I could do something like res0 dot instead of collect, I could do for each. I can do actually, because that's just that, I could just say print And then, so there, I can print it out. And you can see it's not in order because it's distributed. Any other questions? So again, was supposed to be really, really high level. I apologize for near the end, some of the stuff getting mixed up in my slides. But if you want to really get into it, one, I'll be having the session at the end of the month on Mondays, so April 30th and May 7th, I believe. As well as you can see me to give me your information, or even ping me Twitter or whatever. I mean, I'm pretty easy to find because my name is Justin Pahoney. I'm the only Justin Pahoney out there. You Google me, you get my Twitter, my email, justinpahoney@gmail. I mean, I'm not hiding. Ping me and you can ask for 30-day Pluralsight trials and whatnot. All right, thanks.